Okay, let's actually do some numerical examples of these. Where I am pulling this from is page 364. This is the exercise set at the end of section 7.1. I'm going to look at problem 14. We're going to do A and B together. I'm going to let you do C on your own. Pause the video and do it, and then we'll come back and you can hit play again when you're done and see the steps. Make sure you got the answer right. It says a sociologist found that in a sample of 50 retired men, the average number of jobs they had during a lifetime was 7.2. The population standard deviation is 2.1. Understand that in all of the problems in a good portion of Chapter 7, we will be told one of the population parameters, if not more than one. This one we're assuming that we're told the population standard deviation is 2.1. Of those 50 retired men that were surveyed, the sample mean was equal to 7.2 and the number of jobs that they had in their lifetime. The population standard deviation, this one's sigma, not an S, is 2.1. In part A, it says find the best point estimate for the mean. Okay, for the population mean. When we're talking point estimate, the best point estimate is our sample mean, which is 7.2. No computations to be done there, no extra work. They're just wanting to make sure that you understand the sample mean is the best representation for an estimate for the population mean that we have. We don't have any other information. In part B, it wants a 95% confidence interval for the mean. The things we need to know. The only thing up here that we don't have that we need is our z-score, our z sub alpha over 2. If we have a 95% confidence interval from the little box in our book or from the arithmetic that we could do on our own, we will find out that we use the z-score of 1.96. Now our confidence interval is going to be centered around that mean, and we know we're going to subtract the z-score times the standard deviation over the square root of n from that mean, and we're also going to add that same expression back to get our low and our high ends. So from here it's just arithmetic. 7.2 minus 1.96 times 2.1 over the square root of 50, and then we'll go back and do the same thing, adding that same expression to it. So, grabbing my calculator. Looks like we get 6.6 for the low end of our interval, and the high end is going to be 7.8. What we can do is say with 95% confidence that the mean of our population, if we look at all retired men, who knows whether we're looking in the country or state or what, but that the average number of jobs that they've had in their lifetime is 6.6, between 6.6 and 7.8. It's the population mean that we're estimating. We centered this estimate, this interval, around the sample mean that we found. And we can say with 95% confidence that the population mean is between those two values. In part C, it asks you to do the same thing, only it asks you to make an interval using 99% confidence. Go ahead and pause the video now and try that one at your desk, and when you're finished you can hit play again and I'll show you the steps. Okay. For this problem, I lost my z-score, should be 2.58, but my fingers have stuck my pages together. 2.58 for a 99% confidence level. So we start with that same 7.2. We subtract the z-score of 2.58 times the same standard deviation of 2.1 over the square root of 50. That'll be our low end. of our interval, the high end, will be that same stuff with the plus sign in between it. So the low end of that interval should come out to be 6.4. And if we find the high end of the interval, we get 8.0. The rounding rules are all in your textbook. It tells you how to round. If you're starting with the raw data yourself and finding your own mean, your own standard deviation, your own sample statistics for the computation, it tells you that that's different rounding rule than if you're given what the values are in the problem. So go back and read through that paragraph and make sure that you know what the rounding rules are. Notice the relationship here that this interval, when we wanted to be 99% confident, which is even more confident than we were before, that the interval got bigger. It gets a little bit lower on the low end and higher on the high end. It has to encompass more data, so we can clearly say that we are more confident about that. Your book also shows a handful of examples on these, so this is it's a good resource for you if you need to see another written example. Now the other thing might be that we want to go backwards. We know how close we want to be. Maximum error. We know how close we want to be to the actual population mean. We want to be within 1 penny of that mean, or we want to be within 1 year in the age. But we know the error, and we want to know how big a sample we should take in order to get that close. Our maximum error is our z-score times sigma over the square root of n. This is our error. So if we know what the error is, we know how confident we want to be, we know our population standard deviation, then using algebra we can figure out what n has to be in order to make that true. So if I want to solve this equation for n, the first thing we're going to do to both sides is multiply both sides by the square root of n to get it up to the top and get it out of that fraction. If we have the square root of n times e equals, I'm just going to write z because I'm lazy, times sigma, then if I want to solve for n, I need to divide that e over. And then in order to get rid of the square root, I'm going to need to square both sides. If you look at your formula card, it's on there under Chapter 7. You've got your confidence interval. It says z confidence interval. Ignore the t one for now. We'll bring that in later. And then your sample size for the means. So if they tell us how much error we're willing to accept, then we can tell how big a sample we need to use in order to get that close. I'm looking now at number 23 in your exercise set. It says a healthcare professional wishes to estimate the birth weights of infants. How large must the sample be? So we're looking for n. If she desires to be 90% confident, and the true mean is within 2 ounces of the actual sample mean. And we're going to assume again that we know this population parameter, that the standard deviation is 8 ounces. When they tell you how far away from the true mean they want to be, that's your indication that you are given the error. When it says how large a sample do you need, then know that n, the letter n, is what you're trying to find from that. From our 90% confidence, that's going to give us our z-score that we need to plug into the formula up above. And for a 90% confidence interval, z is going to be equal to 1.65. It's actually 1.645, but we'll go with what the book says. This is one of those that's halfway between two values. So if I want to find the sample size, necessary. I take my z-score, I multiply it by the standard deviation, I divide it by the error. I want to be off by no more than 2 ounces with the birth weights, and we're going to square that number. Now, because that will almost never come out as an actual whole number, we're going to have to round. Okay. This turns out to be 6.6. When we square it, we get 43.56. Now, since this represents the minimum sample size that I need to get all of this done, I want to be within 2 ounces of my actual birth weight. No matter what the actual decimal would round to, we're always going to round up. Okay, always round up in this case. Even if it was 43.1, we would round it up to 44. Okay, because I can't have a portion of a person, but I need at least 43 point some, then I know that I have to go up to that next whole number. Okay, even if the decimal would normally round down. So my sample size would have to be 44 or greater in order for me to guarantee that I can be within 2 ounces of the actual birth weight for the population of those babies. Okay. I want you to read through the section. I know I've said that a lot, but it's very important that you read through the section. And in 7.1, the homework I want you to be working on is 12 to 24, counting by threes. I won't pick up anything from 7.1 until after break on that Wednesday, and I possibly won't pick this up with that batch. But your next homework will be due the Wednesday after break. If you have questions about this lecture, if it didn't work for you, send me an email. I won't be near my email through most of spring break, but we can talk when I get back on that Monday, and hopefully this works out okay. So have a good break, and thanks for watching.